Okay, let's go on with section 4.3. This is projectile motion. So we learned in the previous section about two-dimensional motion, and we saw that the object had a horizontal component and a vertical component. So in projectile motion, we're going to utilize what we've just learned. And so we can look at an object in projectile motion. Let's first look at launching an object horizontally. So let's consider first. So suppose we have a platform of height h, and we launch an object with a velocity v in the x direction, so v initial x. So the object is going to travel some distance and land on the ground. So we can say that the distance that the object lands from the base of the platform is given by the letter r, which we shall call range. So we'll say that h is the height of the platform in meters, and then r is the range in meters, and the range is the horizontal range. So one of the things that we can find is we can find, for example, how long it takes the object to reach the ground. Let's call it we can find a time to reach the ground. Okay, so this is the time of flight. So let's say let t be the time of flight. Okay, so we can say that using our kinematic equations, we can say using y final equals y initial plus v initial y delta t, and in this case let me just use t since I'm saying t is the time of flight. So v initial t plus half ay t squared. I'll first draw the vector representation for this object's motion. So we have our initial velocity v initial x, and so this object is going to fly like that. So at some point here it will have v initial x, and then it will have a vertical component vy, and then here we can still have vx. So let me take out the initial and just put x. We'll see why, what I mean by that later. So let's say vx, this is vx, and then it has some velocity like that, vy, and this initial point there is no y velocity. And so for the vertical motion, the acceleration is in the y direction, and this is just equal to the acceleration of gravity g. So vertically we have ay equals g, which is negative 9.8 meters per second squared. So the vertical part of the motion is uniformly accelerated, and then horizontally we have a subscript x. So the x component of the acceleration, a subscript x, is equal to 0. So we are talking of no air resistance. So since there is no air resistance, there is no horizontal acceleration. Okay, so there is no air resistance, so no air resistance in vertical or horizontal direction, of course, but the vertical component is accelerated by gravity. So using our formula, so we know that it falls vertically, so we can say that h is the vertical displacement, and that can be given by half, and we can use negative h if you like, or let's do it this way. Actually, let me do it this way. So I'll say that since going down is 0 and top and the bottom is the final position, that's 0, and initial is h, so that will give us negative y final minus y initial is equal to negative y, and so our y will just be h. Okay, so we can say that negative h is equal to half times negative 9.8 times t squared. Therefore t squared is equal to 2h over g, or 2h over 9.8, I mean 2h over 9.8. So t is equal to just the square root of 2h. So I've taken away the negative sign because I've done the subtraction to go down. So we can say in general, if you want to leave it in symbolic notation, you would just say t is the square root of 2h over g, knowing that when you put in the g, you can remove the negative because you have a negative h there, so there should be no negative square root. Okay, so that's why I worked it out this way for you to see that the negative sign goes away. So I'll leave it in this form as a general formula for us. So that is the time it takes to fall that height h. That time, as you can see, depends only on the height h. It doesn't depend on the velocity at which you launch it. It only depends on the height of the platform h. Any questions on that? So knowing this time, we can now calculate the range. And the range means the horizontal distance traveled. That's the horizontal distance from the base. So we can say that horizontally, let's say that delta x is equal to v initial x delta t plus half ax, and we're not talking of delta t, sorry, let me remove the delta t. This is just regular t, ax t, and this is t squared. So note that ax is equal to 0, okay? So, and also that delta x is equal to r, so we can say that r is equal to v initial x times t. So that's your horizontal range. And so since ax is equal to 0, v final x is equal to v initial x, and we can write that as equal to v. So if you like, we can rewrite this. Instead of using v initial x, we can use v, but I think let's leave it as v initial x for now. Okay, so we've calculated the time it takes to fall and the horizontal range. Those are the important things for launching a projectile horizontally. And one last thing we can calculate is the final velocity of the projectile. Since, so we shall say, what is final velocity when it hits the ground? So we can say to find final velocity, v final y is equal to v initial y plus a subscript y and t, not delta t but t, where t is the time of flight, a subscript y times t. And so v final in the y direction is just equal to g times t. Since v initial y is equal to 0, it was launched horizontally, so the y component is initially 0. Okay, so this is our final velocity, v final in the y direction, and then we have v final x equals v. So we can now calculate v. V is just the square root of vx squared, or v final x squared, plus v final y squared. So that gives us the magnitude of the velocity, and its direction will be given by the tangent inverse of v final y divided by v final x. So the final velocity is v, and it has a component v final y, v final x, and it has a direction tangent inverse of v final y divided by v final x. And to look at it in vector form, suppose we have the platform again. I give you this initial velocity, and then it projects and lands. So this is the floor. What I'm referring to here is this velocity v. So this has a component v final y and v final x, and its direction is given by this direction here. Sorry, that's the wrong direction. The direction is this direction I'm referring to, theta. Any question on that? So that's what I mean by v. Any questions on that? No question. Okay. Let's try an example on that. Okay, so try that exercise. Okay, let's get some of the answers. So the time to reach the ground, anyone with an answer for that? 3.19. Is that what everybody is getting? Okay, so t equals 3.19 seconds, and the formula you use for that is what? Number 2. What is number 2? The horizontal distance traveled. Anyone with an answer? So the range is going to be the horizontal velocity times time, and then number 3, final velocity. So when I'm saying final, I'm talking of the general velocity, the vector v, which has vx and vy. So is that what you did? So v final y is a certain number, v final x you already know, and so when I say v, I'm referring to v final x squared plus v final y squared. So what would that give us? Okay, so we have 58.97 Let's just leave it at 58.9 meters per second. Is everybody getting that? So what is V final Y? And V final X is, so you're going to take the square root of 31.9 squared plus, is everyone clear with that? V final Y is 50. No, V final Y is just about, V final Y is going to be G times T, 31.9, yeah, 31.9. Yeah. So negative 31.9. And V final X is 50. So let me put this formula here, maybe that will help. So V final Y is just going to be equal to G times T, and V final X is still the same because there is no acceleration in the X direction, so it's just 50 meters per second. Okay. So once you get those two, you just put it into the square root formula there, Pythagoras' theorem, to get your final. And what is the direction? So what direction would that be? Okay, 32 degrees, thank you. So you should get into the practice of calculating the vector for when you say when you are dealing with a vector and I say final velocity, I'm referring to the magnitude of the final velocity vector. The direction is given by that. So anytime you deal with vectors, always calculate the magnitude and the direction. Okay, that is our definition for the vector. Calculate magnitude and direction. So it's 58.9 meters per second at 32 degrees. So it's going to hit the ground at that angle. The square root is Vx squared, V final X squared plus V final Y squared. The quantity is V final Y is 31.9, V final X is 50. So the formula for V final Y, and then the last question there was, if the horizontal speed is doubled, what happens to the time to reach the ground? Doesn't affect it because you can see that there is no speed in the time. What about if I double the height? What will happen to the time? Square root of 2, 1.414. So you should think of it that way. When you double the height, it means that you are just putting 2 times h times another 2. So that's just an additional square root of 2 that goes in there. So it increases by a factor of 1.4. You can try that and let's see. So you put 100 meters in there and see what happens. So it's going to be 200 over 9.8. So divide 4.52 by 3.19 and let's see what you get. So the time is determined only by the height from which the object is projected. It doesn't matter how fast you project it, it will fall at it will hit the ground at the same time. Even if you increase the speed, it's still going the same height. Okay. Questions on that? Okay, so let's go to the next thing here, which is project.